This is section 3.4, concavity and the second derivative test. A reminder that concavity is kind of the way that the graph curves. So if a graph is concave up, it sort of curves upward, and if it's concave down, it's sort of curving downward. So if f is a differentiable function on an open interval I, the graph of f is concave up on I if f prime is increasing on the interval, and concave downward if f prime is decreasing on the interval. So we are talking about the rate of change increasing or decreasing. So the rate of change are these tangent lines, right? The slopes of them. Notice it goes from negative to positive to bigger positive. That's concave up. Or from positive to negative to more negative. That's concave down. In the last sections, we found when the graph of f was increasing or decreasing. So how can we relate that to concavity when the f prime is increasing or decreasing? Well, we need the derivative of the derivative to figure out when it's increasing and decreasing. So the test for concavity, f is a function whose second derivative exists on an open interval I. If the second derivative of x is greater than 0, so positive, for all x and I, then the graph of f is concave upward on the interval. If the second derivative is less than 0, so negative, then the graph is concave downward. This is very similar to our increasing and decreasing from the last section, except that it's the second derivative, and that is related to concavity. So let's find the open intervals on which this graph is concave up and concave down. We need the second derivative. So to get the second derivative, we start with the first derivative. And to get this first derivative, I would use the quotient rule. Derivative of the top is 0 times the bottom unchanged minus derivative of the bottom, which is 2x, times the top unchanged, all over the bottom squared. And when I multiply this all out, I get 0 minus 2x times 6 makes negative 12x. And I would actually multiply out the denominator now. X to the 4th power plus 6x squared plus 9. All right, there's my first derivative. That's not helpful to me yet. I need the second derivative. So to get the second derivative, I take the derivative of what I just got using the quotient rule. Derivative of the top is negative 12 times the bottom unchanged minus derivative of the bottom, which is 4x cubed plus 12x, times the top unchanged, all over the bottom squared. So I need to distribute and do some stuff with this to simplify it. I get negative 12x to the 4th power minus 72x squared minus 108 plus 48x to the 4th power plus 144x squared, all over. And I'm going to rewrite this denominator, but I'm going to go back to what it was before, x squared plus 3 squared, then square that again, which makes it x squared plus 3 to the 4th power, just because that's easier to work with at this point in time. So I'm going to combine my like terms. Let's see, I get 36x to the 4th power plus 72x squared minus 108 all over x squared plus 3 to the 4th power. And just like we did with our first derivative, we are going to set that equal to 0. Well, let's see what x can't be first. What would make the denominator 0? Well, I do a 4th root, so I have 0 equals x squared plus 3. Subtract the 3 over, and square root it, I get x equals positive or negative I square root 3. We don't care about imaginary answers here. We're only looking for the real ones. So nothing makes the denominator 0. So remember that for a fraction to equal 0, the numerator must be 0. So I can essentially ignore the denominator now. I find my GCF. I believe my GCF here is 36. Using x to the 4th power plus 2x minus 3. And then I can factor that. Oops, sorry, 2x squared there. And I get 36 Remember to break apart an x to the fourth power, I just go x squared and x squared. I go plus 3 and minus 1. And then I look at my solutions. This first part gives me plus or minus I squared root 3, which we don't care about because it's not real. The second part gives me x is positive or negative 1. Those are my only zeros of the second derivative. Now, just like we did before, I'm going to set up a number line to help me visualize this. Put in those answers. This time we're going to plug it into the second derivative. So I'm going to take a value, let's go here, that's less than negative 1. And I'm actually going to use this factored version in my brain when I do this. So I'm going to treat my second derivative as 36 times x squared plus 3 over times x squared minus 1 over x squared plus 3 to the fourth power. I know the denominator is always going to be positive, so that's helpful. If I plug in negative 2, I get positive times a positive. Negative 2 squared minus 1 is still a positive. I have all positives. My second derivative is positive. If I plug in 0, my denominator is still positive. I get positive times negative, so it's negative. And something bigger than 1, so maybe 2. Positive, positive, positive. All right. Oops. Sorry. So the answer to our problem, I'm talking about the concavity. When this is positive, the second derivative is positive, it is concave up on those intervals, negative infinity to negative 1 or 1 to infinity. And it is concave down on negative 1 to 1. Oops. There we go. And there's our answer. Let's try another one. We're going to determine the open intervals on which this is concave up and concave down. So step 1 is find the first derivative. I'm going to try to write a little smaller on this one. So I take derivative of the top, which is 2x, times the bottom unchanged, minus derivative of the bottom, which is 2x, times the top unchanged, all over the bottom squared. Simplify this a bit, I get 2x cubed minus 8x minus 2x cubed minus 2x. And let's make this x to the fourth power minus 8x squared plus 16. And continue simplifying, I get negative 10x over x to the fourth power minus 8x squared plus 16. There's my first derivative. But I don't need the first derivative, I need the second derivative. So let's find our second derivative. Derivative of the top is negative 10 times the bottom unchanged, minus derivative of the bottom, which is 4x cubed minus 16x, times the top unchanged, all over the bottom squared. And for the bottom squared, I'm just going to go back to this original one, x squared minus 4 squared, and square that. Now let's distribute in that numerator. I get negative 10x to the fourth power plus 80x squared minus 160 plus 40x to the fourth power minus 160x squared all over x squared minus 4 to the fourth power. And when I combine my like terms, I get 30x to the fourth power minus 80x squared minus 160 all over x squared minus 4 to the fourth power. And I'm going to set that equal to 0. This time I do have numbers that x cannot equal, where the derivative doesn't exist. Those would be x can't equal positive or negative 2. And if I look back at my original function, those are actually asymptotes of the graph. So I'm just going to write that down. Those are asymptotes because the function's not continuous there. Let's find anywhere else that the function equals 0. We're going to set the numerator equal to 0. When I set that numerator equal to 0, I'm going to start by taking out a 10 right away. 3x to the fourth power minus 8x squared minus 16 now. Those numbers are a bit easier to work with. I'm going to try to factor this. The only way to break apart 3x to the fourth power is 3x squared and x squared. So let's see, I need numbers that multiply to 16 and I get an 8 there. We're going to go 4 and 4, minus and plus. Well, 3x squared plus 4 doesn't give me any real solutions. X squared minus 4 gives me positive or negative 2, which, look at that, those are my asymptotes anyway. All right, let's set up our intervals. Negative 2 and positive 2 are the places that I could switch concavity. I'm going to plug in my values to the second derivative this time. So I pick a value less than negative 2. Let's say negative 3. We know the denominator is going to be positive because it's to a fourth power, so I just care about the numerator. If I plug in negative 3, I get a positive, it's positive. If I plugged in 0, I get a positive, a negative. If I plug in positive 3, I get positive, positive. So that means my graph is concave up on the intervals negative infinity to negative 2 and 2 to infinity. And it is concave down on negative 2 to 2. I promise not every graph is set up like this where it's concave up, concave down, concave up. Now for a new vocab word, points of inflection. Let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at the point c, f of c, then this point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or downward to upward at the point. So if the first derivative exists at this point, that's what this says if it has a tangent line. If the first derivative exists, then we have a point of inflection, but only if the concavity changes there. Sometimes the concavity doesn't change. But here we have 3 pictures of points of inflections because the concavity changes, concavity changes, concavity changes. Our theorem on points of inflection: if c, f of c is a point of inflection of the graph of f, then either the second derivative is 0 or the second derivative doesn't exist there. But remember, the first derivative must exist there if it's a point of inflection. So these are very similar to our critical numbers, except that with the second derivative. So let's determine the points of inflection and the concavity of this graph. So first thing, find those points of inflection, which is setting the second derivative equal to 0. So let's find the first derivative. It is 4x cubed minus 12x squared. Look at that, much simpler when it's not a fraction. Then we find the second derivative, which is 12x squared minus 24x. Now to find our points of inflection, we set that second derivative equal to 0. I'm going to dive right in and factor out a 12x, leaving me x minus 2. My numbers here are 0 and 2. These are my possible points of inflection, POI, points of inflection. These aren't guaranteed to be points of inflection like with critical numbers. Critical numbers, if you set the first derivative equal to 0 and solve, that is a critical number. Points of inflection, we aren't guaranteed. We have to check whether the concavity changes. Also, we have to make sure that the first derivative exists at both of those. It does because it's a polynomial. All right, so 0 and 2. We're going to plug in some test values to the second derivative. Let's say I plug in negative 1. I get a negative times a negative, so positive. Let's say positive 1. I get a positive times a negative. And positive 3, positive, positive. There we go. The graph switches from positive to negative, concave up to concave down, and then concave down to concave up. So both of these are points of inflection. So our points of inflection, which remember you can shorten to POI if you want. 0 and 2 are my x values. Plug those into the original to get the coordinate. If I plug in 0, I get 0. If I plug in 2, I get 16 minus 4 times 8, 16 minus 32, negative 16. Doing those in my head here. And then it also says discuss the concavity. When it says discuss the concavity, it just means tell me where it's concave up and concave down. It is concave up on the interval negative infinity to 0 and the interval 2 to infinity. It is concave down on the interval 0 to 2. And there we are. Ooh, down. No. Now we have the second derivative test. The first derivative test was where we checked the first derivative, set it equal to 0, and we said, okay, if the graph goes from increasing to decreasing, we have a maximum, relative maximum. If the graph goes from decreasing to increasing, we have a relative minimum. The second derivative test, we have a function, and the first derivative equals 0. This is a key piece here. We still set the first derivative equal to 0. The second derivative has to exist on an open interval containing that value. If the second derivative is positive, then that point is a minimum, relative minimum. If the second derivative is negative, then that point is a relative maximum. And if the second derivative is 0, then the test just doesn't work, and we don't know. It might be a max, it might be a min, it might be neither. So basically what this says, if my graph is concave up, that point has to be a minimum. And if my graph is concave down, that point has to be a maximum. So let's use the second derivative test. Please realize you'll almost never be told which test you have to use, first derivative or second derivative. It's your choice. So let's do this. We take the first derivative, which is 15x to the 4th power plus 15x squared. Now we're also going to need to find the critical numbers. Remember, critical numbers are setting the derivative equal to 0. Let's factor out a 15x squared. Leaves me x squared plus 1. I get x equals 0, and x equals positive or negative I. My only critical number is 0. Then, if we're using the second derivative test, we need the second derivative. F double prime of x is 60x cubed plus 30x. For the second derivative test, we just take this critical number and plug it into the second derivative. The second derivative of 0 is 0. Sadly, on this one, second derivative test fails. We can't actually use the second derivative test on this one, which stinks. So that means we have to go back to the first derivative test, which is where we set up our number line, put in our critical number, and we're going to evaluate the first derivative on either side of that critical number. So the first derivative at a number less than 0 is positive. The first derivative at a number greater than 0 is positive. Well, that's why the second derivative test failed. There are no relative maxes or mins on this